right, next in our latest line of videos that 4 of you will watch, we are going to talk today about limits again. It's been a while, but we're going to revisit it now that we have some more tools at our disposal. So we'll start with a problem where if I want to look at the limit of x goes to 3 of x squared minus x minus 6 over x minus 3. Now, one of the things we did when we were looking at limits, most of the time we were dealing with continuous functions. So we tried just plugging stuff in and seeing if we got an answer. And in this case, if we plug in 3, we get 3 squared minus 3 minus 6, and 3 minus 3 in the denominator, and we get 0 over 0. So when we were first learning limits, this told us that we needed to work harder. And in that case, we knew what we could do. We could actually go ahead and factor our numerator and denominator and try to see if anything canceled. And that happens here because this factors as x minus 3 and x plus 2 in the numerator. And then we have x minus 3 in the denominator. And so from there, we are able to cancel the x minus 3, and now this becomes the limit as x goes to 3 of just x plus 2. And now when we plug that in, we just get 5. Okay. So when we tried to plug stuff in and we got 0 over 0, it was an indication that we needed to work harder somehow. So let's look at another example here. So now let's look at the limit as x approaches pi over 2 from the right of the function cosine of x over 1 minus sine of x. And we see that if we just go ahead and plug in that value, that pi over 2 there, because these functions are right and left continuous, here we would get 0. And when we have 1 minus sine of pi over 2, we have then 0 over 1 minus 1. So we do again get 0 over 0. Now you can't divide by 0, so this isn't an answer, and we can't necessarily conclude that this limit doesn't exist. What it means is what it meant up here, which is we have to work harder. Okay, this is what we would call an 0 over 0 is an indeterminate form. And whenever we get an indeterminate form, it means we're going to have to call on other techniques to solve it. We have techniques available to us to solve the first one. For the second one, we're going to need to introduce something new, and we're going to introduce that in a second here. But we're first going to look at another couple of types of problems. So example 3, again, is a problem that we've sort of looked at before. And we get 4 minus 2x minus 1. Okay. And again, you try to think about what happens as x goes to infinity here. And if this goes off to infinity, well, that numerator is going to go off to infinity. That's just going to keep growing because this is some quadratic that is opening upwards. So that's going to go off to infinity. And the same thing with the denominator. It's also a quadratic opening upwards. But again, we learned a technique for dealing with this. So when this was our case, when we had this sort of rational function, what our strategy was to multiply by a fancy 1. We took the highest power of the x that appeared in the denominator and divide the top and bottom by that power. So we had 1 over x squared on both of these. And when we did that, we would distribute and simplify, and we'd get 3 and then plus 6 over x plus 9 over x squared. And then on the bottom, we get 4 minus 2 over x minus 1 over x squared. And then when we evaluate these limits, what we have happening is these parts with the x in the denominator go to 0, and we're left with the limit is just going to be 3/4. So when we got infinity over infinity, it meant we had to work harder. We weren't able to just plug something in and had to use some other bit of terminology and theory. Along the same lines, we could have a limit as x goes to infinity of something like ln of x and have that quantity squared. and then just over x. And if we think about this, as x goes to infinity, well, the ln of x is going off to infinity, so in an abusive notation, we've got like something going off to infinity squared. So that's really just infinity over infinity here. So again, I don't know what this limit is. I could maybe do a numeric guess, but there's no algebraic way of doing it. And again, this is infinity over infinity is another example of what we call an indeterminate form, meaning, well, that just knowing that about the limit doesn't tell me what the limit is. It means I'm going to have to work harder to do it. And the tool that is going to help us here is going to be what's called L'Hopital's rule. And so we would say, suppose f and g are differentiable and g prime of x is not equal to 0. Open interval I that contains a point A. Then we're going to suppose further that the limit as x approaches A of f of x equals 0 and limit as x approaches A of g of x equals 0, or that the limit as x approaches A of f of x equals infinity and that g of x is the same thing. So then the limit as x approaches A of f of x divided by g of x is equal to the limit as x approaches A of their derivatives, f prime of x and g prime of x. And so what this is doing is giving us a tool for how to go about answering questions about limits for these indeterminate forms. And you can see why you don't want g prime of x to be 0 because of it's showing up in the denominator here. So let's go ahead and look at these examples that we've already done using this new technology. So we went back up and we saw that the limit here was 5 before, but we could have also gone ahead and used L'Hopital's rule on this. And so we're just going to make a note here that we know that this answer is 5. So what L'Hopital's rule is going to tell us is that the limit of x going to 3 of this thing, since it's 0 over 0, it's that indeterminate form, well, I can take the derivative of the top and those limits are going to be the same. So the derivative of the top here is 2x minus 1, and then the derivative of the bottom is 1. And now the limit as x approaches 3 of 2x minus 1, I can actually just plug that in, and I get 2 times 3 minus 1, and I get that same 5 that we got before. So this even works on these other limits that we had learned earlier. So now let's look at this other one that we have. So we see that it's indeterminate. Now, according to our L'Hopital's rule, this will equal the limit as x approaches pi over 2 from the right. And in L'Hopital's rule, it says as you approach A, but all of the things that it says work for left-hand limits, right-hand limits, and limits at infinity. So those are all true as well. So what we're going to do is take cosine of x prime, and we're going to multiply by 1 over sine of x prime. So we're going to take those derivatives. That's probably the last time I'll write it out that way. So as we approach pi over 2 from the right, okay, so derivative of cosine is negative sine of x. And then in the bottom, we have 1 minus the sine of x. So the derivative of the 1 is 0, and then we'll have minus cosine of x. And so now we try to evaluate again. And when we plug in pi over 2, we actually get something that's defined here. So this will be the negative sine of pi over 2 over the negative cosine of pi over 2. And if we're thinking about that, this is going to be 1 and this is 0. So when this happens, because of this, we've got a 1 in the numerator and a 0 in the denominator. That means we're going to have some sort of vertical asymptote. And that's where this approaching from the right is going to make a difference. So as we approach from the right, if we just clean this up just a titch here, this will be sine of x over cosine of x. As we approach pi over 2 from the right, the sine value is positive and the cosine value is also positive, so this is going to go off to positive infinity. Now, along these same lines as before, we can, with this infinity over infinity indeterminate form, we could go ahead and use L'Hopital's rule to do this. So we could take the limit as x goes to infinity. And now we take the derivative of the top, which would be 6x plus 6, and that 9 goes away. So I'll put the 0 there in this case. And then the derivative of the bottom will be 8x minus 2 minus 0. At this point, we would look at this and try to plug in infinity or think about what happens at infinity. So this is actually infinity over infinity again. So we would have to use L'Hopital's rule again. And whenever I use L'Hopital's rule, I like to just make a little note over the equal sign there. And I just label it with an L-hop here, is what I usually will say. And so now we take the derivative again of the numerator. And so we take the derivative and we just get 6 plus 0. And then we get 8 minus 0, which equals, now as x goes to infinity, there is no x anymore. We just get 6/8, which is equal to this 3/4. Now for the one that we have not done yet along these lines, again, it's indeterminate in this case because we have infinity over infinity, so we're going to use L'Hopital's rule. So we'll take the derivative of the top, in which case we will need to use the chain rule. So we have 2 times the ln of x, and then we take the derivative of the inside, we get 1 over x. And then when we take the derivative of the bottom, we just get 1. So if we're going to clean this up, this is the limit as x goes to infinity of 2 ln of x over x. And again, if we try to think about what happens as we go to infinity, we get another infinity over infinity here. So we use L'Hopital's rule again. And in the top, we are just going to get 2 times 1 over x. And in the bottom, we get 1. So now we have the limit as x goes to infinity of 2 over x. And as x goes to infinity, this limit is going to be 0. So L'Hopital's rule gives us a way to use derivatives to answer questions about limits of the form, these indeterminate forms of infinity over infinity and 0 over 0. And in our next videos, we'll talk about other indeterminate forms and how we can use L'Hopital's rule to answer those questions as well.